Hi, Untitled is my name. I did a similar recording before showing how to calculate internal forces inside the beam in a quick way just by looking at the system, and that's basically the same thing I'm going to do here. The only difference that this video is going to be in English. So basically when you got a system and you cut the system, there are internal forces that you're gonna be able to represent as they're shown here. So the first one, you got normal forces. They're basically tangential to the length of the beam. The other one are shear forces. Here the symbol for it is Q, but that's come from the German Querkraft, but actually we use V in the English notation, and M is for the Bendy Moments. So normal forces basically have two possible signs. It's negative when the beam is being pressed, stressed under compression, and it's positive when the beam is being elongated, so when it's under tension. For shear forces, there's actually a convention too. It's positive on the right side of the cut downwards, on the left side upwards, and negative when we just switch those directions. But as a rule of thumb, what I will tell you here for the calculation of shear forces is basically to weight your beam from the right to the left, so not from the left to the right. Just look at the beam from the right to the left, and every time that you got any forces perpendicular to the length of the beam, you just draw a jump in the direction of that force with the value of the force basically. Okay, so if we look at the example we have here, we're basically gonna have on the left pin support a half of the value of the craft there in the middle upwards. On the right for the supports, we're gonna have half of that same force upwards too. And if we hit the beam from the right to the left, we're gonna have a jump upwards with the value F, a half of F. Let's say half of F is like a half of the value of the force. Then it's continuous because we don't have any force or any distributed load. Then it jump downwards to with the value of F. Okay, and then constant, and on the left pin support it jump up half of F again upwards. Then the second case is basically the distributed load, and what happens with the distributed load is basically the same thing. On the left you're gonna have here half of the resultant of the distributed load, and on the right the other half. So if we hit the beam from the right to the left, gonna have a jump on the right holding support, a jump with the value of half the resultant, and then what we have here is a linear distribution of the shear forces caused by the distributed load. Okay, so it's basically going downwards because of the distributed load we have up there. And the last internal forces we need to think about here are bendy moments. So what happens with bendy moments? Let's say the easiest way to draw bendy moments is just to imagine how your beam is gonna deform. So what's gonna be the deflection curve? And when you can picture the deflection curve, you can easily know on which side the moment is gonna be, depending on where the tension is. So I'm gonna try to explain it. Let's look at the example we have here. A single load on the middle of the beam. This beam is gonna bend downwards. What I mean with that is that the point there, the middle of the beam, is gonna have a deflection going downwards. But the left and right furthest position of the beam, so on both supports, are not gonna move. So we're basically gonna have an arch opened upward, and that is actually what we call a negative curvature. So that arch opened upward is a negative curvature, and the opposite of it will be a positive curvature. So when you have a negative curvature, the tension side is downward. So you can actually imagine that the lower line of the beam is going to be stressed a little bit more than the upper one, or we can actually say that the upper one is going to be under compression while the lower one is going to be under tension. So the tension side is downwards. So let's look at the last example we have here. It's basically a distributed load. How is the beam going to be deformed? What's going to be the deflection line? The deflection line is exactly the same as above. Okay, it's just that the value of the deflection is not going to be the same, but it's irrelevant here. It's not the most important thing. So the beam will deform exactly like this blue line over here. This blue line is actually the bending moment distribution, but the deflection will be exactly the same. So it's basically bended upward. So we have like a deflection downward, but it's open to the to the upper side, basically. So this is like a negative curvature, meaning positive bending moment. Yeah, I have other videos where I actually explain in further detail what's happening there, but that's gonna be it for now. And now we need to look at the different kind of forces we can actually have on the system. We can have like a single load here on the left, a single moment, or a distributed load. So basically what happens with single loads is that we have jumps in the shear forces distribution, shear forces distribution, and a technique like a sudden change, a jump in the slope of the moment distribution. That's what single loads do. For single moments, what happens is we get a jump in the moment distribution, and for distributed load, we are completely on the right. What we get is a linear distribution in the shear forces, in the shear force diagram, and a quadratic distribution in the moment diagram. Okay, and now here we just want to look at some kind of supports. We have like the hollow supports. This is the upper one with just one force upwards. It could be upwards or downwards, doesn't really matter. And the pin support with two reaction forces, and then the clamp support with all three reaction forces. Those are all the supports we can actually okay, not all of them, but those are the the supports we generally get in a 2G case. So let's go and try to actually solve something with all what we've learned. Start. So in this case, we have like on the right a compression force, but moment is not about compression, it's just about curvature. Because of that force on the right, what's going to happen is the right end of the beam is going to bend downwards. In the general case, we're going to get here a positive curvature. Okay, so it's bended and open downwards, it's a positive curvature. So the moment is actually negative, and negative for us here is above. That line down there is actually the positive side. Okay, and on the other side is the negative one. So here's the answer. Normal forces, it's just about compression or tension. So the force here that's perpendicular to the beam is irrelevant for normal forces. The only one that's relevant is the right one, the one that's horizontal and pointing to the right. And what is that force doing to the beam? That force is putting the beam under compression. So we're gonna have a negative normal force here, a negative normal distribution. Like I said again, the interrupted lines down there indicates the positive side. So it's not like in math where positive is above and negative is below. Here it's basically the opposite. So now what do we have here? We have a distributed load. It's not a constantly distributed load, but it's still a distributed load. What's going to happen is on the left side we have a pin support. We can't have any deflection there. On the right side we have a holding support, no deflection either. And in the middle we're going to have a deflection downwards. That's going to be a negative curvature, meaning a positive bending moment. Now positive, this could be this one or that one, but you can also see that since the distributed load is not constant, we cannot have like the same change of the slope. It should be a little bit more here towards the right. That's why it's the right answer. Okay, shear forces. We have like a single load in the middle of the beam. What's going to happen on the left side with the pin support, as well as on the right side with the roller support, we're going to have forces upwards. Their value is basically half of the single load that's there applied on the middle of the beam. So wheeling the beam from the right to the left, what's going to happen? I'm going to have a jump upwards from half of F. Then it's going to stay constant up to the middle of the beam, then it jump downwards with the value of F, and then constant again. The left one here can be right because it's not a distributed load we have there, so it's this one here in the middle, the answer. Here bending moment, what's going to happen? It's very similar to a case we had before. The right end of the cantilever beam here is going to be bended downwards, so we're going to have a deflection downwards, meaning that the curvature we give will be open downwards. That's like a positive curvature, meaning a negative moment. What we have to know here, two negative moments, so it can be the left answer here, it can only be the middle one or the right one. Now the force is at the end of the clamp of the cantilever beam, so the moment there should be 0. We don't have any single moment there, so yes, the answer in the middle. Now normal force is here. We have like an inclined load. This inclined load can basically have two parts. We can have like a vertical part that's more important for shear forces, but we don't need shear forces here, and we have a horizontal part that's basically directed to the right here. So what's that force gonna do? That force is basically gonna put the left part of the beam under tension. The left part of the beam, so it's not 0, it's not continuous because we have like a single load here, it's not a distributed load in length direction, so here's the answer. And that's it for the first level.